So, have you ever wondered why your phone and, say, a deep space satellite can't just use the same tiny clock to keep time? Well, it turns out that in the world of electronics, clocks aren't just about ticking away. It's all about trade offs. Think of it like a performance ladder. As you climb higher, you get absolutely incredible precision, but, and this is a big but, every single step up comes with a cost.
All right, so in this explainer, we're going to climb that very ladder. We'll kick things off with the basic XO, then step up to the tunable VCXO, the all-weather TCXO, and finally the powerhouse OCXO. And then we'll wrap it up by figuring out how you actually choose the right one for the job.
Right, so let's get into it. This whole thing is basically a climb. With every rung we go up on this oscillator ladder, we get better and better timing. But you guessed it, that precision always costs you something, whether it's power, size, or just plain old money. It's a really cool balancing act.
So, really, why all the complexity? I mean, why do we need so many different kinds? Well, it's because every single electronic system has a different job to do. A simple little gadget, it just needs a basic pulse. But a 5G tower, that needs to sync perfectly with a massive network. And a satellite, it has to keep time in the, incredibly harsh environment of space. Each one of these oscillators is like a specialized tool designed for a very specific job.
Okay, let's start our climb right at the bottom rung. We're talking about the XO. This is the most fundamental, the most basic type of oscillator you'll find. You can think of it as the simple, steady metronome that provides the basic heartbeat for just countless electronic devices. So the XO, or Simple Packaged Crystal Oscillator, is pretty much exactly what it sounds like. It's the no-frills workhorse of the timing world. Seriously, it's just a quartz crystal and a basic circuit, all sealed up in one package. There are no fancy tricks here. Its stability? That depends entirely on the raw, natural properties of that little slice of quartz. And because they are the most cost-effective solution, I mean, by far, XOs are, well, they're everywhere. They've got this huge slice of the market, providing that essential clock signal from millions and millions of microprocessors and digital systems that just need a basic, reliable pulse to do their thing. Okay, so what does that stability actually look like in the real world? We're talking about plus or minus 10 to 50 parts per million, or ppm. Now, what that means is, for every million ticks of the clock, its timing could drift by up to 50 ticks, especially as temperatures change. For a lot of devices, that's totally fine, good enough. But what if you need more control than that? And that very question brings us to the next rung on our ladder. See, if you need to fine-tune a frequency, or maybe lock onto an external signal, you're going to need a different kind of tool. Enter the voltage-controlled crystal oscillator, or VCXO for short. The best way to think about this one is as an XO, but with an electronic tuning dial. By feeding it a specific control voltage, you can actually pull the crystal's frequency a little bit up or a little bit down. And this is absolutely critical for things like network gear, where you have to lock your device's clock perfectly onto an incoming data stream. But this introduces a really fascinating trade-off. Engineers call it the pullability paradox. And here's the deal. The more you want to be able to tune that frequency, the wider you make its pulling range, the more you have to give up the crystal's natural built-in stability. It's a classic engineering problem, right? You just can't have maximum flexibility and maximum stability at the exact same time. All right, so we've covered basic timing and then fine-tuning. The next huge challenge for engineers is temperature. As electronics heat up and cool down, a crystal's frequency just naturally drifts. So the question is, how do you keep a clock stable when it's inside, say, a hot car or on a cold mountaintop powering a radio? The solution is ingenious. It's the temperature-compensated crystal oscillator, or TCXO. Just think of a TCXO as having a tiny, smart thermostat built right inside. It has a little temperature sensor and a special compensation circuit that are always working together. They measure the temperature and then apply a corrective voltage to keep the frequency locked in no matter what the weather's doing outside. And the payoff for this is, well, it's huge. Just look at the jump on this chart. That active compensation makes a TCXO something like 20 times more stable than a basic XO. That is a massive leap in performance, and it's what makes precise timing possible in devices that have to work anywhere in any condition. So this amazing mix of good stability, small size, and low power draw, it makes TCXOs the perfect choice for our modern portable world. They are literally the timing heart beating inside our cell phones, our GPS units, and that whole exploding universe of IoT and wearable gadgets. Okay, so we figured out how to compensate for temperature. But what if compensation just isn't enough?
What if your application demands something close to perfect, totally unshakable precision? For that, my friends, we have to climb to the very top of the ladder.
Welcome to the top. This is the oven-controlled crystal oscillator, or OCXO, and the concept here is it's just brilliantly simple. Instead of just compensating for temperature changes, an OCXO eliminates them altogether. It literally puts the crystal inside a tiny insulated oven, heats it up to the one temperature where it's most stable, and just keeps it there. It doesn't fight the weather, it creates its own perfect little climate.
And the result? It's just staggering. An OCXO can be over 1,000 times more stable than a plain old XO. We're not even talking about parts per million anymore. Now we're talking about parts per billion. This is the level of precision you need for the absolute backbone of our modern world. Things like 5G base stations, satellite communications, and super high-end scientific gear. So there you have it. We've climbed the whole ladder, from the simple XO all the way up to the ultra-precise OCXO. Let's bring this all together and see how an engineer actually makes the call on which one to use, because in the end, it really is all about making the right trade-off. Okay, this chart right here, this is the whole story in one place. As you go from left to right, from the XO to the OCXO, just watch that stability number, it gets exponentially better. But that precision comes at a very clear cost. See how power use, size, and cost all shoot up? That high power use for the OCXO, yeah, that's literally the energy bill you pay for running that tiny internal oven 24/7.
And here's how all of this plays out in the actual market. You can see that basic XOs, the SPXOs, still take up the biggest piece of the pie, just by sheer numbers. They're the workhorses, for sure. But the real story here is in the growth. The fastest growing parts of the market, that's the high-performance TCXOs and the SC cut-based devices, which are often used in OCXOs. And that demand is being driven directly by things like 5G rolling out, advanced driver assistance systems in cars, and all this other next-gen tech that absolutely has to have that higher stability.
And this really gets to the core of it all. It's like the quote says, "Selecting an oscillator is a complex optimization problem. There is no single best oscillator. There's only the best one for the job." It forces a designer to sit down and decide what's most important. Is it cost? Is it size? Is it power consumption? Or is it that unshakable top-tier precision? So, the next time you hear about some big leap in technology, a brand new satellite network, a faster phone, a smarter car, you'll know that deep down inside it, there's a tiny clock ticking away. And now you'll also know that an engineer had to make a really careful choice from this ladder we just climbed. They had to perfectly balance cost, power, and size, all against one critical question: just how perfect does that taking really need to be?